And let's get this party started, I guess. Okay. So, okay, so something that I'm just going to put it up here, something that Dr. Pillai had gone over for this as like a little review that was helpful. Let me just move this up a little bit more. Was for electrocyclic. We had 4N, which is conrotatory, which means Mobius is allowed, right? And then, oops, the last part, 4N plus 2, disrotatory, Huckel allowed, right? And then versus cycloaddition, we have similar, right? 4N supra-antra, and this is Mobius. Mobius is allowed, and then the 4N plus 2 is the supra-supra, which is Huckel, right? So these are just things to remember as you're running through. These are just patterns to think about, right? Okay, so for the following reactions, give the arrow pushing to account for electrocyclic ring opening and also the number of electrons involved in the reaction. B, it's not split up differently, but whatever. For the number of electrons you give in the answer, would that many electrons be Huckel loop, aromatic, non-aromatic, or anti-aromatic? For the number of electrons you give in the answer, would that many electrons in the Mobius loop be aromatic, non-aromatic, anti-aromatic? State whether the allowed electrocyclic ring opening would be conrotatory, disrotatory, and would proceed via Huckel or Mobius transition state. Draw the allowed product, right? So in this one, we have how many electrons are participating in this opening. Anybody? Nobody? All right, one, two. Oh, sorry.
Yeah, no, yeah, that's what I was gonna say, so it's fine.
Okay, cool. So we have 4 electrons, which means what?
On and Mobius.
Yep, conrotatory, exactly. Mobius. Okay, so then we have our open ring, which we will have our double bonds here. And then, so what's going to happen with our methyl groups?
They're going to be opposite.
What do you mean? Can you use the terms inside, outside for an open and then up or down for a closed?
Okay, so 1 in and 1 out.
1 in, 1 out. Okay, perfect. And this is because this is up and up, correct? So we're moving them conrotatory, which means in the same direction. So if you had your 2 thumbs up in front of you and you move them both clockwise or both counterclockwise, you would have one pointing to the, you would have them both pointing to the right or both pointing to the left, right? So for this Mobius loop, this is aromatic, right? Because this is a 4N system. So the Mobius is your allowed aromatic. Perfect. So same thing for this one. How many electrons are participating in this reaction for B?
6.
6, yep, exactly. So 1, 2, 3 times 2 electrons each, right? And I always say 1, 2, 3, 4, 5, 6. Count your electrons so you don't lose any. I mean, your carbon, sorry, 1, 2. I don't want to lose any carbon. So 1, 2, 3, 4, 5, 6 carbons, right? Sorry, I don't know why my pen's being all squiggly, but there's my 6 carbons. Okay, and then so we have 6 electrons, which means this is what kind of system? 4N or 4N plus 2?
4N plus 2.
4N plus 2, which means what? Huckel or mobile? Mobius. Mobile.
Huckel.
Huckel, yeah, exactly. and which makes this an aromatic as well, right? Because this is our alkyl system. We have the aromatic because it's, you know, we have all sp2 in their conjugated systems, right? And then for our methyl groups, what are we doing with our methyl groups?
One is gonna be up and down because or one's in and one's out since that's how they were already.
Yeah, so one, I'm gonna put this one out and this one in because of how my drawing is. I don't want it to like look like it's an extension. Yeah, so one in, one out because we have one up, one down, and it's moving in. Oh, we didn't identify. We said 4n plus 2, but 4n plus 2 means what? That it moves in what direction? Conrotatory or disrotatory?
Disrotatory.
Disrotatory, exactly. So disrotatory means they move in opposite directions. So if you have one up and one down, you have one moving clockwise, one moving counterclockwise, whatever, you get it. So you have one on each side. Okay, perfect. So now we have our cycloaddition. So remember that's this piece of it, right? Oopsies. Let's go back. There we go. Okay, so give the arrow pushing for the provided cycloaddition reaction and the number of electrons involved in the reaction. State whether the allowed cycloaddition reaction would be super or super antra and would proceed via Huckel and Mobius. Draw the allowed product of the reaction, indicate any chiral centers, and state whether the solution of the product would be optically active or not, and give a brief explanation as to why. So how many electrons are a part of this reaction?
Sorry, 6.
6, yes. So we have 1, because we always start with our negative, right? We always start with our negative charge here. So we have extra electrons, so to speak. So 1, 2, 3. We kick this over here. Perfect. And then, so we would have, let me just draw these little bad boys, right? So this is where our new bonds are going to be. Perfect. Okay. And then we will draw our 5. Let me see. I'm going to draw my oxygen first so I don't mess that up. Okay. And then they all just we have no more formal charges. Initially, we had a negative and a positive here. We don't have those anymore. And then what about our nitriles? What's going on with these?
One is gonna be up and one down
Why do you say that?
because they're both facing the same way right now. So since it's Huckel, they are disrotatory.
Yeah, so 4n plus 2, which is disrotatory, and it is a Huckel loop. I just want to write down everything you just said. And then, so Huckel loop is what? Super or super intra? Super, right. So with this on your dieno file, so everything except for the directionality, right? So on your dieno file, which is this section up here, right? Because this is a cis dieno file, which means that both of the groups are on the same side, that means that they will also be on the same side when we add them into our product drawing, because it's a super, so it's attacking from one side, right? As opposed to super antra, they're attacking from opposite sides. So a trans would give us a wedge and a dash, but a cis would give us either 2 wedges or 2 dashes, right?
Okay, yeah, because the last one was trans at first. Never mind. Or was
Yeah.
already opposite. Okay.
Yeah. Yep. So with this one, we would do, so our nitrile groups would be on the same side. And then how many chiral centers do we have?
2.
How many? Sorry.
2.
2 plus.
Oh,
That's okay. So there's 4 chiral centers. So these are all chiral centers.
Okay.
And what is this? This one's obviously not a chiral center because it has O's on both sides, right? This one is a chiral center because it has 4 different, right? Same with this one. Even though these two are the same, they're both each a chiral center, and same with these two. Even though they're both the same, they're both chiral centers. Does that make sense?
Yeah.
So there's 4 total, 2 types of chiral centers, but 4 total. And then what do we want? What do we say about optically active or not? And why or why not? I'm gonna give you a hint.
It's
So
not.
then it's a meso compound. It's not.
Yeah. Inactive, right? Yep, exactly. Everybody sees why, right? The mirror image. Anybody have any questions so far?
Mhm.
All right, all right. So with these ones, so the best way that she explained it, let me just move this down a little bit so I have some space to write. Okay, so the best way to kind of think about this, so we're asking for classify the following structures as aromatic, non-aromatic, or anti-aromatic. Assume all structures are as flat as possible and give the number of electrons involved in the conjugated system. So we're looking for cyclic, conjugated, and planar, right? So if it's all of these things, yes. Actually, let me do green for yes, right? So if it's all of these things, yes. Then what? Then what are our options? So we either have a 4N system, which means anti-aromatic, right? Or we have a 4N plus 2 system, which is aromatic, right? So far, so good. Everybody agree?
Yeah.
And then if it's not these things, then it's just non-aromatic, right? So these will be our these will be our keys as we go through. Okay, so we've got our legend, AAA or NA. What do you guys think? Start with A.
That one's not, or is anti-aromatic,
How many electrons?
or
Oops, 4N. 4 electrons. Yep, which is a 4N system. Cool. B.
that one's aromatic, right? No, that's not, because there's 4 electrons still.
4 electrons. Yep, which means
Anti-aromatic.
yep. See, just keep going. Anybody can shout out the answers. You guys got this. Y'all are smart.
That one's aromatic. That's 2, so it's 4N and then N is 0.
So 2 electrons. I'll give you
Yeah.
that one.
Or is that one not aromatic or non-aromatic?
Yeah, why?
Because it's not a conjugated system.
Yeah, exactly. Why isn't it a conjugated system?
Because there's the sp3 hybridized one.
Yeah, exactly. Exactly. Everybody see that? So, oh, this is non-aromatic. There we go. Cool. All right, D. I start with how many electrons first?
There's 8. Wait. 6. 10. So that one,
Yep.
is that one aromatic? Because that you
Mm.
could conjugate it with those, right?
Yep, exactly. Yep. Yeah, those lone pairs are considered part of the conjugation. E.
Non-aromatic.
Yes. Why? How many electrons first?
There's 4, but it's not conjugated. There's
Yeah.
that one, the sp3
Yep.
one.
Yeah, exactly. Yep. F.
Does anybody else want to do them?
Yeah, anybody can hop in, anybody.
Okay, so that one's aromatic.
How many electrons?
There's 2.
G,
So I got on her office hours earlier, and the part that we're skipping are the ones that have a different atom that's not carbon. So she skipped
you
over
guys
all
are
of them.
lucky, lucky. Okay. Well, just so you guys know, this would be 6 electrons, aromatic, right? So I'm just gonna go over it quickly, just in case you guys see it, because you guys don't have it in this class, if any of you guys are going to med school or something, or taking something, you just might see it somewhere else. So 6 electrons, aromatic, right? Same thing with this one, 6 electrons, aromatic. This one is 6 electrons because you have 1, 2, and then this nitrogen has a lone pair and a double bond. It can only donate one of them. It's going to do the double bond, right? But it can only do one or the other. So again, aromatic. Same thing here, 6 electrons because of the double bond. It's going to do the double bond over the lone pair. So same thing, 6 electrons, aromatic, right? This one again, 6 electrons, aromatic. This one we have 10 electrons, 2, 4, 6, 8, and then 10 aromatic. Right. This one here we have 10 electrons again. 1, 2, 3, 4. Oh wait, 5 times 2, 10. Like, what am I saying? Aromatic. And then this one, this is 4 electron system. And it is non-aromatic because it's a non-conjugated system. So just, quick review of that, just so if you see it at some other point in time in your life. Okay, so then that means that you guys probably wouldn't do this, I assume. Are you guys doing anything with like identifying lower pKa's?
Yeah, so she did that, but it would be like without the nitrogen, but then it would be the one that is the benzene ring is the stronger one, so that one has the lower pKa, right?
The benzene ring that's strong.
The aromatic, sorry, the aromatic, not stronger, is like the more stable one.
Yeah, exactly. Yeah, exactly. So, yeah, the way that is a good way to think about it, because I don't know exactly what her material is, but I just to like kind of think about this, like this is asking like what's your lower peak, which one's expected to have a lower pKa, which means more acidic, right? And so when you're reducing something, it's like what one wants to like give up its hydrogen, right? And so with this, we would have this if we were to like, plus H plus. And with this one, oops, too much stuff. With this one, we would have this one plus H plus, right? And so basically like how you want to think about that is like, this first one here is non-aromatic because it's a non-conjugated system, right? This one is aromatic, right? Because we have a conjugated system. When you dissociate the hydrogen from it, you then have an aromatic structure because it can donate these lone pairs to the ring, right? Giving it that conjugated system. This is still just an aromatic structure, right? So we're going from non-aromatic to aromatic versus we're just going from aromatic to aromatic. So it's not much change going on in the second structure here as far as stability. Whereas going from non-aromatic to aromatic, that's increasing the stability because of the aromaticity. So A is a better, has more reducing energy because it will lower the pKa. So it's more acidic. It will readily donate that proton because it will be aromatic when it does. So just to give you guys a way to like think about some of that stuff. I know this, you might not see this exact structure, but just to give a way to like think about it is like, what kind of product do you, or what kind of structure do you have in the beginning? Non-aromatic, anti-aromatic, aromatic. What do you have at the end? Same, right? And like, if you're going from non-aromatic to aromatic, that is it's going to want to do that, right? Because it's increasing its stability. If it goes from aromatic or non-aromatic to anti-aromatic, it's not going to want to do that because you're decreasing stability, you're increasing instability, right? So there's some ways to think about those problems.
Wait, Sarah, can I
so-
just ask a question?
Yeah.
Wait, so sorry, can you just explain briefly again? You mentioned that like one of them, is a conjugated system and the other isn't. What are you looking at that like tells you that distinction?
Oh, like here, this is non-conjugated, right? It's non-aromatic because there's no nitrogen isn't donating anything to the, it's non-conjugated. It's positively charged, right? So it's not donating to the ring at all. So there is no conjugation, right? This is an sp3 hybridized, right?
Right.
Versus
Oh, I see. I thought you
Ye-
meant between the two and black on the top.
Oh, no. Well, I mean, also like, these are two separate structures, right? This is, A.
But I
and
mean, like
B.
they're both not conjugated, right?
No, this one's conjugated. See?
But like, what is the nitrogen? So like the nitrogen is donating the electron in the double bond. That's all.
Yes, exactly. Nitrogen
Okay.
can do, I know, and you guys haven't seen this in the material, and you probably won't, which is why I'm saying, it might not look exactly like this, but just to give you guys some context, right? It's like nitrogen can donate either its lone pair or its bonded electrons into a system. So if it, in this example, only has a double bond here, then it can donate that into the system and create that conjugation. Whereas over here, it has no lone pairs and no double bond to donate, which makes this a non-conjugated system. Whereas here now in this second structure, once we've dissociated the hydrogen, right, now we have a lone pair that can contribute to this system, making it conjugated. Does that make sense?
Yeah, thank you for clarifying.
Yeah, no problem. Okay, so with this one, we have consider the structures of the following alkyl bromides. Do you guys have this at all? You must, because it's bromine. Anyway, which compound would you expect to undergo SN1 process most readily, and justify your answer? So what happens in an SN1? Like, what's the first thing that has to happen in an SN1 reaction?
This stuff confuses me a lot, so I don't.
No worries,
Yeah.
no worries. So the leaving group has to leave, right? It's not a concerted reaction like SN2 or E2. Concerted reaction, remember, everything happens at the same time. Versus SN1 and E1, you end up with a carbocation intermediate, right? And this is stuff that we covered at the end of OChem 1, right? And it's going to keep coming back and keep coming back, like all these concepts will, right? So in an SN1 reaction, our leaving group has to leave. Well, what's our leaving group on all of these?
Bromine.
Right, yeah, exactly. And it says this, right? Our alkyl bromides, right? So what are all of our carbocations going to look like, right? So we're going to have...
So would C leave then because it would become aromatic? Most readily.
Second, let me just draw this out real quick. I wish I was better at multitasking for this, but I don't want to miss a carbon or a bond or something. I know I will.
Okay.
Okay, perfect. So So yeah, so let's go with, you know, fastest to slowest. Okay. Okay, so you were saying,
Oh, C, because it would become aromatic. Or-
C is what? Fastest or slowest?
Fastest, but it's
So
not
if,
because it's 4 electrons. But it's conjugated now, right?
so C will actually be anti-aromatic. It's not conjugated. It doesn't have the electrons to donate here. So because remember, this was an sp3 hybridized. So
Okay.
all of these are sp3 hybridized, right? And so this doesn't have any electrons to donate to it. So this is did I say non-aromatic or anti-aromatic? Sorry. Anti-aromatic. Sorry. I was thinking about this one over here. But anyway, okay. So anti-aromatic, yes. 4N system. 4N. Yes, they're all, well, not all of them are conjugated. This is conjugated. So okay, so let's just start with this. What are all of these, right? They're all the same thing, right? What are they? Oh, are they all aromatic, non-aromatic, anti-aromatic?
Anti-aromatic or non-aromatic?
Yeah, because we have these, right? sp3s.
Yeah.
So sp3, so they're all non-aromatic. Sorry, that's what I was saying, like non-aromatic.
Oh,
I
I'm
was
sorry,
talking
the
about this.
beginning ones are. I was looking at
Yes. These ones up here, the beginning ones, right? Starting ones. That's why I was getting confused. And I said non-aromatic at first because I was like, wait, what? Okay, so yes. So this, yes, it would be a conjugated system with C, the carbocation version would be conjugated system, but it would be anti-aromatic because it's 4 electron system, right? And then
Yeah.
what about this one? What about B? I know you guys can't see my
So
pointer
then
either.
B would be aromatic then because it has 2 electrons from the oxygen?
Yes, aromatic, exactly. So
The
this would be
fastest.
6 electrons total. And then what about A?
That one's anti-aromatic too with the 4. But it's non-aromatic because that's sp3.
Yeah, exactly. So we're going from all of our products or rather all of our reactants are non-aromatic. And now we're going to either non-aromatic or anti. So which one will be the fastest
Would
and which
B
one
be
will
the
be the slowest?
fastest because it like wants to be aromatic?
Yeah, exactly. And which one's the slowest?
C, oh, the slowest would be A because it doesn't change. Or B, or C, I mean, because they don't want to be.
Yeah, because if you're going, doesn't matter if you're going from non-aromatic or aromatic, nothing is ever going to want to go anti-aromatic, right? Doesn't matter what your starting product is, starting reactant is. Nothing wants to go anti-aromatic because that's so unstable. Like non-aromatic is more stable than anti-aromatic. Does that make sense?
Okay, yeah.
So so in this case, if ever you see anti-aromatic, just know right away, like that is like, nobody wants that, right?
Okay.
Cool. Any questions on this so far?
No.
Okay, everybody else feeling good? Okay, so number 6 says one equivalent of HCl will preferentially protonate one of the nitrogen atoms and not the other. Give a brief explanation of your choice of product. So protonate means it's going to add a hydrogen to it, right? So we have, oh gosh, I hate drawing pentanes. I always mess them up. And we have our hydrogen here. And then for this one, same deal. Okay, then we have our hydrogen here, right? And the only difference really is just these. So which one, you know, I guess like what are you starting with and what are you ending with, right? So let's just say this is A and this is B, you know. I start with A, like what, you know, are your beginning reactant, what is this? How many electrons are within the system? Like, is it conjugated or not? I guess start with that.
Well, would the 2 from the nitrogen be in the system or
It
no?
would.
Okay, so
Yeah.
then that's aromatic.
Yeah, so there's 6 electrons, and so it's aromatic, right? And what about B?
It's non-aromatic.
Yeah, non-aromatic because there's no conjugated system, right?
Yeah.
So, and then what about the product? What about product A?
It's non-aromatic. It's not conjugated.
And what about product B?
It's not. It's still not aromatic.
Yeah, exactly. So we're going from aromatic to non-aromatic and non-aromatic to non-aromatic. So which one will be preferentially protonated?
B, because it's less stable than A.
Not because it's less stable, but because it's your well, I guess A would be it's a less stable move, right? This is like no change, right? No change. Non-aromatic to non-aromatic. This, you're decreasing its stability because you've taken away the aromaticity because these lone pairs participate in that conjugated system. So if we protonate it, then we no longer have that conjugated system, right?
Yeah.
Cool.
Sorry, can I just
yeah,
ask a question?
please do.
Wait, so how do you know that the product for the first one is non-aromatic? Can you just explain that again?
Yeah, conjugated systems. So remember, conjugated systems is every other, right? You have some form of like electron that's, or, you know, space that can be, you know, because obviously, as we saw up here, it can also be a formal charge, right? As a
I
part of
just
an
thought you said that the nitrogen has to like have electrons to contribute or something, and that's how
It
you know.
does. Yeah, it does. This one has the electrons to contribute. This one doesn't because this electron no longer has these electrons to
Oh,
contribute
yeah,
to the system.
okay. Okay, okay, I see now.
Yeah, these are 2 different systems, remember?
No, yeah, yeah. Okay, yeah, thank you.
Yeah, no problem. Yeah. Okay. The fun part, right? Synthesis. Okay, what do you guys think? Talk to me. What is KMNO4, you know, HO or OH, whatever? What does that do? Anybody remember? Okay, so we're going to remember it. Oops, what's going on? Does this ring a bell to anybody? I'm just gonna take my sweatshirt off real quick while you guys think about it, or maybe look in your notes. Okay, sorry, my headphones were off. If anybody said anything. Benzylic hydroxyls. Does this ring a bell? No? Okay. So what we'll end up doing is we will break this off and we will have our benzene ring, and then we will have And then, remember that this is our acid workup step, right? So we're just adding carboxylic acid on there. That's it.
So
Okay.
just basically opening it.
Yeah, exactly. Yep. Just adding carboxylic acid to it, through the acid workup step, right? What about this next one? We're reducing, right? We're going from oxygen, more bonds to oxygen to less bonds to oxygen. Anybody? This is the easy one. All right, who's got their review sheet? Who's got if you guys aren't comfortable with these, you got to have your summary of reactions out. So that way you don't, because that's like, honestly, that's key. If you don't know it right off the top of your head, just look at your reaction summary until you start to memorize this stuff and recognize these, right? Because you don't want to, here's the thing, if you just, you look at a reaction and you can't figure it out, you're just going to kind of reinforce that I don't know statement in your head versus if you're like, I don't really recognize this. Let me look at my answer key let me look at my reaction summary real quick, figure it out. Oh, okay, yeah, this is this one, right? You start to create that pathway of like, oh yeah, when I see this, it's this. When I see this, it's this, right? You got to reinforce that into your brain, right? Oh, do you guys have the reaction summary on your exam? No.
No,
Okay.
she just has a list of like the reagents.
Well, yeah, I mean, that's kind of, yeah. I mean, that's very helpful, so, but yeah, go
Wait,
ahead.
is it, I'm not sure, but is it the lithium aluminum hydride or the sodium borohydride?
Those reduce ketones and aldehydes
Okay.
specifically.
Okay.
So this one is our, remember, H2 PDC, right? And then it just reduces everything straight down, doesn't matter what it is. So it reduces functional groups in general, right? Reduces functional groups, doesn't have specificity, right? Those other ones do, they kind of have more specificity. So this is going from a nitro to an amine, right? What about this next one? C. What are we doing? What are
Oh,
we
we're
doing?
like eliminating the what is that? Ketone?
So a ketone is what, turning into our hydrocarbon, right? CH2. That's what this is. CH2. So what does this? Clemmensen reduction reaction? Anybody? Right? Ketones or aldehydes, right? Also aldehydes, right?
Is that a 2NHG?
I'm sorry, no, that's a Z.
Oh, Z, okay.
Z. Or I could do.
Wait, sorry. You know, in the last one, when I said those other reagents and you said,
Yeah, lithium. Yeah. Go ahead.
yeah. Wait, so you said, those go from which? I thought that was a ketone. You said like a ketone to an aldehyde or something?
No, yeah, it reduces ketones and aldehydes. We're gonna see it in this next one. But
So then
this
how do
one,
you know that those ones can't be applied to number C or letter C?
so it reduces ketones to alcohols and aldehydes to, I guess, is it all the way? So remember that NaBH4 is less strong, right? So it's you know, it's a weaker reducing agent, right? So that one won't reduce all the way, whereas the lithium aluminum hydride, I'm just trying to bring up my reaction keys as well, because I don't want to misspeak. Do we remember? Does it go all the way? All the way. This is too far. That's H2. Oh, is it? Is that from last semester? Last session? Oh, excess. Oh, yeah. No. Yeah, these just go to an alcohol. Okay, it doesn't reduce it all the way. This just reduces it to an alcohol. That's what I thought. So yeah, so the two that you mentioned is just to an alcohol. So it's ketones, aldehydes. So remember so the difference is, so, okay, so for this one, because this is part of this example, right? So we're going, so what's the difference between these two, right? We're going from here to here, right? So we're going from a ketone, right, to an alcohol, okay? So like you said, we could do sodium borohydride, right? Or we could also do lithium aluminum hydride. Oops. I don't know why I did that. Right? So, but the difference here, no, wait, Li. Yeah, that's right. That's correct. Okay. So the difference here is that this one will do ketones and aldehydes, whereas this one will do ketones, aldehydes, and esters, right? That's the difference between the two. So either one of these would be correct. You're going from some sort of, it's a reducing agent, right? You're going from some sort of ketone, aldehyde, ester, right, to an alcohol in particular, right? Whereas up here in B, these don't work for sodium borohydride and lithium aluminum hydride don't work for nitro groups, amines, you know, so it doesn't work for nitro groups. It's specific to that that functional group. So that's why we chose H2 PDC, because it reduces all functional groups. Doesn't matter what it is. It will reduce it all the way to just relationships with hydrogen, right? Okay, so for E, what are we seeing in E? We have two products, right? So we have a product here and we have a product here. What does that mean? You guys remember? You guys obviously are doing this part, right? I didn't like totally mess that up. The positions from your donating groups. Do you guys remember what your positions are? Begins with an O, an M, a P. Anybody?
Yeah, she like went over that, but I honestly, that confuses me a lot. Is this one because that's an electron donating group, right? So then it'll go to the ortho or the para. Is that why it's in those two spots?
Yep. So these are ortho. Whoops. These are meta. And this is para. And so donating groups do orthopara and withdrawing groups do meta, right? And you guys need to know this for your synthesis stuff. So this is why it's super important. So like Danielle said, right, we can tell that our groups have now been added to our ortho and para positions, because like she said, this is a donating group. It's a weak donating group, but it's a donating group nonetheless, right? So that's how they ended up on there. So what do we do for a reaction? What are we adding?
The ether or ethyl group. Is that methyl?
Ethyl group's there already, see?
Oh,
beginning
sorry,
and
we're
the end.
adding the nitrate oxygen thing. I don't know.
Yeah.
How do you say that?
It's a
Like-
it's a nitration reaction. Yeah, yeah, right. I know the amines, I know nitrile, and NO2 is like yeah. I don't know. I don't know
Okay,
exactly.
yeah, that one.
Yeah, that one. Yeah, it's a nitration reaction anyway. Let me see. Yeah, nitrogen dioxide, I guess. No. But yeah, so we're doing, so how do we add, so what's a you know, a nitration reaction? Like what do we have to use to add those? These are catalysts, right? It's not really a part of the reaction, it's just helping to move things along, right? Okay. All right, there's more. Oh, and there's more. Okay, so what's going on? What are we doing here? What are we doing? What is this?
What was, I was sorry, I was looking at something else, but what was the can you scroll up for a second so I can finish writing down that reagent? Okay, it's HS2. Okay. Okay, thank you.
Yeah, it's just a catalyst. Yep. Yep. All right, what are we doing here? Right. So what is this? What's this this group here? What functional group is that? Let's start with this. Do you guys remember what the functional group is? Nitrile. Right. Is it a donating group or withdrawing group? Does anybody remember my hint about how to figure out if something's a withdrawing group or a donating group?
Is that
Does
one a
anybody-
withdrawing group?
Yes, it is a withdrawing group. Why?
Because it doesn't have the extra like lone pairs. Right?
I mean, yeah, I guess you could say that, but it's not necessarily the only reason why. But so my biggest hint is figuring out if something's a withdrawing group or a donating group is from the ring
Mhm.
that you have two positions, right? So say we have a ring here, you have two positions, you have position number 1 and position number 2, right? And then I'm going to draw, this is the benzene ring, right? Benzene ring, right? Benzene ring. Okay, and then I'm going to draw another one, you know, over here. So we have position number 1 and position number 2. So if whatever is in position number 1 is more electronegative than what's in position number 2, then it will be a donating group.
Okay.
But if whatever is in position number 2 is more electronegative than position number 1, then it will be a withdrawing group, right? Because it's pulling the it's more electronegative, so it's pulling the electrons away from the ring. Does that make sense?
Yeah.
Now, there is obviously exceptions to, in particular with oxygen, right? Because think about if you had a ring and you were double bonded here, is this a withdrawing group or a donating group?
Donating, withdrawing, sorry.
Yeah, withdrawing, right? Because it can't donate any more electrons that way. The only way the electrons can go is away from it, right? So there are obviously a few exceptions to that rule, right? Or like if carbon had a negative charge to it or something, you know, there's a few like, you know, but generally speaking, you can assume that it will probably be a withdrawing group if the more electronegative carbon is further away from in the second position from the ring, versus the other way around, right? So those are some ways to think about this stuff. So in F, we're back to here. This is a withdrawing group. It's a nitrile. So what do withdrawing groups do? Ortho, para, meta.
The meta position?
Meta position, yeah. So meta positions, okay. So I'm going to redraw. I'm going to try to stay consistent with where these bonds are. And then, yeah, we just literally just add a bromine onto either one. It does not matter. Okay, what about G? What do we have? We have two groups here. We have this group here and we have this group here. Group A, is it a withdrawing group or a donating group?
Withdrawing.
Is this more electronegative than this?
Oh, I'm sorry. I was looking at group B. That's never mind.
Yeah,
Is it
donating group.
donating? Okay.
Yeah. And what about this one? What about B?
Is B withdrawing then because it has oxygen?
Yep, withdrawing group. Yep, exactly. So whenever you are trying to decide on where to put something, it's like your reaction is always going to listen to your donating group before it'll listen to your withdrawing group, because obviously it's donating electrons and electrons are required to have a reaction, correct? So always prioritize your donating group over your withdrawing group, right? So in that case, we will add what and where?
To the ortho, because the para is already taken.
Yeah, exactly. So what are we adding?
The Cl, the chlorine or whatever, Cl.
Check your reaction summaries.
Oh, I have no idea then, because these are not my favorite things.
Right, so it's gonna have to be in one of these positions. We decided. Does anybody know what we're adding? We're just adding an aldehyde. Right. Okay. What about this one? We have two groups again. We got a group here and we got a group here. What do you guys think? Group A, group B, who are we listening to and why? Group A, donating or withdrawing?
Withdrawing?
Would you look?
Oh, donating?
Yeah,
Is it
donating group.
cheaper?
Yeah,
Okay.
exactly. What about group B?
I have no idea.
Group B is also donating group, right? It's just a methyl. It's a carbon. It's also a donating group. Which one's stronger?
The one with the oxygen?
Yeah, right. It's got more lone pairs to give, right? It's more willing to move stuff around. Okay, cool. So this one's a stronger donating group. So what does that mean?
It's gonna go para or ortho, or yeah, para or ortho to that one.
What are we adding?
Harper, you're not gonna do that. No. Oh no, Harper, hold on.
What are we adding? Obviously, we're not going to add it to this position because it's already taken. So I'm going to get rid of that. So we're adding something to this position here, and we're adding something to this position here. What are we adding? We're adding this, right? Is that what we're adding? And then we reacted with this to get rid of the Cl. And so here we have right? Let me do this to make this clear. Okay, so far so good?
Mm-hmm.
All right, what about this next one? What do we have? We have two different rings. So we've got A And we've got B. What's going on? A, withdrawing or donating?
Donating,
Yep. What about B, withdrawing or donating?
withdrawing,
Yep. All right, so who are we gonna listen to?
the donating group.
Yep, which means what for positions?
It would have to go in para or ortho because para's already taken.
That's right. Exactly. So, all right, and then what are we adding?
The NO3.
Yes, but it's not going to be NO3.
Is it gonna be NO2 then?
Yeah, exactly. Yeah, exactly.
Coming right back, Harper.
H3. Okay, perfect. And then we decided it doesn't matter. You can put it wherever you want, right? So NO2. Okay, so it's in that position. Okay, what's up next? What's up next? Okay, so J, right? So J, we've got a couple things going on. We have A, whoopsies, A, and we have B. What do you guys think? A, withdrawing or donating?
Withdrawing.
This is a
Oh,
carbon.
sorry. I'm sorry, is donating. I was looking at B. I keep looking at the wrong one.
No,
Stop
you're
it.
fine. Don't worry about it. B, withdrawing or donating?
Withdrawing.
Yeah, remember we discussed this right when we started, is that the only way that these electrons can go are away from it, right? So there are a couple exceptions to the rule, but yeah, so obviously we're going to listen to our what? Donating group. So that means that what? Got to go ortho para, and para is already taken, so it's got to go in one of the ortho positions. So
You
as
guys
I
still
draw
want
out this,
to go to bed.
as I draw out this hideous structure, tell me what we're adding. Oh gosh. Let me make this a little bit smaller because we have two steps, right? We've got step 1 and step 2. Okay, so step 1, we're adding what? We just did it.
The NO2.
Yeah. Okay, so we're adding the NO2 anywhere. Well, not anywhere. Either of your ortho positions, I should say. Okay, and then second step is what? We did this earlier. What does this do? What does this reagent do?
Where is it? Changes it to NH2.
It's a reduction reaction, right? So step 2 would be all of this the same, blah, 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 right? I'm just going to say etc. Sorry, because the only thing that's changing is just this NH2. Okay, I did this backwards, that's why. What is going on? Oxygen. Oxygen, right? Okay, and there's obviously a continuation of the molecule over here, but I'm just not getting it in because this is what matters. This is what you get with number 2, right? We get that reduction, right? So we're going from this to this, okay? That's the difference. And then last but not least, right? Jackie, we talked about this earlier. Oh, no, this isn't the same one. Sorry, just kidding. Okay, this is a fun one though. A little challenging, right? So what do we have going on here? So it's another two-step reaction, right? Another two-step, right? Another two-step reaction. Okay, So step one, what's happening? What does this do?
It adds the carbon with the hydrogen and the oxygen.
Yeah, we get this Friedel-Crafts reaction, right? So this and this go away. So then what do we end up having?
No
Right?
more.
Oops. Let me go this way. Yeah, so we end up having this double ring system, right? Because we had 1, 2, 3, 4, 5, 6, right? So we're making this connection between 1 and 6, right? So that's how we end up with this ring system. And then what does 2 do? Right, with 2. So with 2, we're just taking off this ketone here, right? So we end up with this. Okay. So it's just our Friedel-Crafts reaction, creating that second ring, and then we remove our ketone. All right. So how are y'all feeling about nomenclature? Do we just want to go through it real quick?
Sure.
Okay, so benzoic acid, what's that mean?
It is a benzene ring with the CHO, right?
Yeah, COOH. Or whoops, sorry, CHO. Okay, and then what about the rest of this? We've got 2 bromo and 5 nitro, right?
So on one of the para ones, or the sorry, the ortho ones, it would be bromo, and then on the bottom, yeah, that one, it would be the NO2.
Yeah, exactly. Yep. All right, what about this next one? Benzaldehyde.
That's a benzene ring with like an aldehyde on it.
Oh yeah, no, I had this. Yeah.
Yeah, I think I messed that one
Yeah,
up.
there we go. Yeah. No, because I remember there was an aldehyde on one of these, but I got the 2 confused.
Sorry.
But yeah. This one's the CHO for the aldehyde, right?
Okay,
and then
and then
the acid is the, right, because it's
so then on 3 and 4, so one of the meta ones and then the para one, it would have 2 ethyls.
one of the meta and the para. 1, yeah, 2. To make that clear. Yep. That's it, right? Our diethyl, right? On 3 and 4. So 1, 2, 3, 4, right? And then what about this one? The IPAC. What do we have?
That one, because it's the OH.
Yeah, so we'll start our numbering here, and then where would we go? Where would 2 be? Would 2 be the chlorine or the nitro?
The chlorine.
Yeah.
And then, yeah.
Yep.
I don't remember what
So
the OH one's name is though, because there's a name for that one.
yeah, phenyl.
Oh, okay, yeah, that's what it is. So then it would be 2 or like 2,3 dichloro
Oops.
and then nitrophenol.
So 2, 3. What did you say? 2, 3 what?
Dichloro,
Yeah, dichloro.
and then 6 nitrophenol.
Yeah. And no dashes here because it's all part of that last name, right? So,
Yeah.
cool. So let's see. Coming towards the end, we're actually making pretty good time compared to last time. Okay. Are you guys doing this where you have to make your you have to generate your electrophiles?
I have no idea. We did not get that far with her on the off-cells earlier.
Got it. Is she doing review or is she just like whatever if you come with
She's
questions?
just like doing whatever questions you have, but we
Got it.
basically just did the like aromatic section earlier.
Got it. Okay. I keep forgetting to look at what might be discluded.
Yeah, I just know that like there was a couple in there that had the nitrogen instead of a carbon in the ring, and she said that that one, those were just like not being tested.
Okay, aromatic section 3, aromatic heterocycles. Okay, which is this, but that's I think it. So changes have been made to the merger, like blah, 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 blah. Okay, all right. I just want to make sure I wasn't doing too much. Okay, so but nobody else has gotten this far in the videos to know whether or not you guys are making the electrophiles. Okay, well, whatever. We'll go through them because you probably will do them, I hope. And if not, you've at least seen it before in your life. So that way, if you get tested on it some other time, you kind of know what's going on. So, okay, so first we have to generate our electrophile, right? So this is what we use to generate our electrophile, right? So let's just start off with that. So we have this. Okay, and then we have plus HCl, HCl, and so I should do this, I should separate them. I think it's glitching out a little bit. Okay, so anyway, so we have these, and I'll try to do my stuff different. So the oxygen is going to come over and steal this, and this is going to go over here and steal that. And then we're going to end up with this oxygen, right, with its, right, and it becomes a good leaving group, remember? So then what we end up with is this electrophile, right, plus H2O, okay? So that's how we generate our electrophile. And then, oops, I was supposed to be doing these curved arrows in purple, sorry about that. And then don't forget to do Lewis base, Bronsted base, Lewis acid, Bronsted acid. I don't know if she takes off points for not labeling that stuff, but Dr. Pillai definitely did, as some of you might have remembered. Okay, so then now we have our electrophile, right? So now what are we gonna do with it? So what is this right here? What kind of group is this? Is it donating or withdrawing? That's what I'm asking.
Oh, withdrawing? Donating, sorry.
Donating, perfect. So it's I think in these ones too, she was saying that it's specifically asking for the para position, not meta. Not ortho. Although I'm not exactly sure why, because it doesn't say it where I could read in these instructions, but I do, because I watched her office hours again before our office hours right now, just to make sure that I wasn't missing anything. So yeah, so she did say that these were going to be para. So we'll just, we're just going to assume para. So this is the position that we'll add it. So now we bring in our electrophile, and so we will have this coming here, which will give us, okay, I'm going to come down here so we can hopefully make room. Okay, so we have, I'm going to try to write kind of small because we have resonance structures. Okay, so when this electrophile attaches, obviously we'll be using the electrons from this bond. So we have a positive here, and then we have our two double bonds still here. So our resonance structures, right? We all remember how to accomplish resonance structures. So this is why they're super important. Let me switch back to the blue. Okay, so we have this. And then, so this is here, then this is here, this. Okay, this is supposed to be a plus. There. Okay, this here, plus. Okay, and then what color did I use? Green. Okay, so then this one will go here. And then we will have this. Or actually, let me do it this way. Let me do these. I'm gonna do these ones. Okay. It doesn't matter as long as you write them all in, but and then so we have our so we have this, this. No, wait. This is supposed to be, oh, I shouldn't have this on here. Oh yeah, no, that's right. 1, 2, 3, 4, 5. Yeah, okay, that's right. And then back to my green. Now say we, right, these go back here, and then, oh, I'm missing these right here. Like, where'd these go? And then these go here, right? And then we get our final. We get our final resonance structure. This stuff is always what takes so long. As you guys know, we have this here, this here, this here, this here. Right? Awesome. Okay. I don't think I missed anything. So then what ends up happening with all of our resonance structures, remember our brackets, then we have, remember we had this chlorine from before, and so we're going to come back in the chlorine. Remember we have this, no, let me draw this in a different color. We have this hydrogen here, right? This is a secret hydrogen. Okay, and we're going to take this hydrogen, and then these are going to get donated this way so that we end up with our final structure. I'm just going to cut it through here. Right? Anybody have any questions about that? I know it's a lot of drawing and a lot of steps. Anybody? Feeling good? Feeling good?
I'm good.
Okay. All right. Well, let's go on to the next one. Let's make our electric generator electrophile, right? So we're gonna have this and our HCl, right? And then so we're gonna have, oh crap, I didn't go through. Reminder, right? Lewis acid, Lewis base, Lewis base, Bronsted base, Lewis acid, Bronsted acid, right? Just as a reminder. Okay, so anyway, so then Lewis base, oopsies, Bronsted base, Lewis acid, Bronsted acid, right? Okay, so then what we have is we have this 1, 2, and then we have, because remember, our carbocation is not going to go on the end, right? We're not going to have it on a primary, but is this the most stable carbocation? Or could it go somewhere else? What do you guys think? We're going to have a hydride shift, right? Because the carbocation is more stable at a tertiary intermediate. I mean, tertiary carbon, right? That's why we see this hydride shift, which you wouldn't draw it in, but I'm just showing it to you, right? So there's our electrophile. Okay. So then we add our electrophile to our benzene ring. And so then this would be, we have this come in here. Okay, and then so we'd have our resonance structures. I'm just drawing this over here so it's out of my way. 1, 2, 3. Okay, and then we have the positive here. And then we have this here and this here and this here. And then 1, 2, final 1. This here, this positive here. These are formal charges. Wait, whoops, too far. Too far. Sorry, right here. Okay, so those are all of our possible resonance structures. And then again, we're going to bring in that Cl. And it's going to come in and take our hydrogen, and this is going to go here to fill that in so that we get our benzene ring back, right? And then if we go through and we do Lewis base, Lewis acid accepts electrons, and then we have our Lewis acid, Bronson acid, Lewis base, Bronson base, right? Because a hydrogen is involved. Anybody have any questions about that? Feeling good? So we're basically, all we're doing is we're generating our electrophile. Our Lewis base is attacking our Lewis acid. We're working through our resonance to find, because you're going to be given the final product, right? And then you're just creating that aromatic ring again, right? Because on all of these, we have like the cation, the formal charge, right? So we're just creating our benzene ring. That's all we're doing. Generating electrophile, Lewis base attacking Lewis acid, going through resonance structures, aromatic ring. Okay, should we do one more? How you guys feeling? What do you guys think?
I'm good.
Good. Does anybody else want to see one more, or are we good? Yes, no,
I'm
thumbs
good,
up,
but it's
thumbs
up
up.
to you guys.
Nobody's saying anything, so I'm just going to assume that you guys are good. Okay. So, but if you guys want more help with that, you can always feel free to reach out to me. Okay, so for this one, choose the slowest and fastest position indicated by the arrow for the electrophilic aromatic substitution. So these are our positions that we are looking at. Okay. So for okay, so for number 1, What are we looking at? We've got this and we've got this. What do you guys think? What's the nitrile group? Donating or withdrawing?
Donating,
And what's the aldehyde?
withdrawing,
Withdrawing. Cool. So what are we gonna listen to?
the donating group.
Yeah. So we listen to the donating group because we want to know what the electrophilic aromatic substitution is going to be the fastest on, right? So where are we going to have the fastest reactions happening at? So we already know it's going to be our donating group over our withdrawing group. So if our donating group, where do we have the fastest reactions at?
So A.
Yeah,
Number
ortho and para. Yeah. This one's going to be the fastest. Then what?
Then would C be the slowest, and then B would B be the middle because it's still the donating group, or would it be the slowest because that's not the one that it likes to do?
Nope,
It
it would
does-
still be, it would be the middle because, yeah, because at the end of the day, the slowest is always gonna be your withdrawing group. So good rule to think of is like number one is always gonna be your donating groups and it's gonna preferentiate orthopara, but then it'll take meta. And then number two will be your withdrawing groups, right? So, which will be, because this, remember this deactivates your ring, right? And then typically it will go on meta over the other two, right? And then it will orthopara, right?
Okay.
So these are like your general, like, if this, right? This is like the checklist that you go down. Cool. So what about this one? So we have a couple of things going on here. So this alcohol, what do you guys think? What's going on with this alcohol? Yep.
And
Donating
then
group.
the one's withdrawing. So would it be B is the fastest, then A, and then C?
B is the fastest,
Then A.
middle, whoops, middle, whatever you get it, slowest. Yeah, exactly. Yep. Because you also want to kind of look at it like this, right? So this is obviously going to be your withdrawing group here. This is going to be your stronger donating group, right? Between the two. So yeah. So you're going to listen to your donating group first. It's going to be your para, excuse me. And then obviously, again, like we said, your meta will come before your withdrawing group here. So, which is also a meta. So even though withdrawing groups prefer meta, we will see the donating group meta before the withdrawing group meta. Because again, the withdrawing group deactivates the ring. Whoops. Okay, this is the last thing. There's just three synthesis problems. So show how you make the target molecule from the provided starting structure, show all intermediate structures, don't show any mechanisms. If other isomers are formed at any step, then you need to indicate this, but you don't have to draw their structure. So AKA you can just do a plus minus, right? That's all that means. Okay, so what do you guys think? So this is when your reaction summaries would be really helpful, right?
Are you
go
gonna be you're posting this like tonight by chance?
Oh
or,
yeah, yeah. As soon as this is done, I'm gonna it takes a little bit of time to like save, and then I have to upload it, which takes time. But usually I post the links right away. It's just that the links don't necessarily work right away because it's still uploading to YouTube. But you will at least have the links on
pop off
page.
then and just watch it. I have a 4-year-old and a 2-year-old, and they've been brushing their teeth for like 10 minutes. So I'm a little worried to
Don't
go see
even
their
worry
bathroom
about it.
right now.
Yeah, exactly. No, I get it. I also have a 3-year-old and a 1-year-old, so I understand.
Bye. Thank you.
Bye. Yeah, no problem. Okay, so we have so on here our what are like basically the two differences here, right? So we've added these two, right? We've added pro, right, and the chlorine, right? So those are the things that we've done that we've changed with our benzene ring, right? So as far as these two are concerned, what position are they from each other? Right? What position are they from each other?
Ortho and meta?
They're both meta from each other. So from the chlorine, this prop is meta, and from the prop, this chlorine is meta. Do you see that?
Oh, okay, okay.
Yeah, so they'll be the same position from each other either way.
Okay, okay.
Yeah.
Thank you.
So yeah, of course. So how do we make how do we add something in the meta position? With a withdrawing group or a donating group?
A donating group? I'm not exactly sure.
Yeah, that's okay. Yeah, so in order to get a meta position, it has to be a withdrawing group. So and in this case, right, that means that this had to have been a withdrawing group at one time. I'm sorry, not this one. What am I saying? So, because, okay, so the other thing too is like with halogens, they're typically going to be donating groups. And I'll show you guys more about that with the next one. But they're going to be ortho and para directing. Not that they're going to be no donating group, but halogens are typically ortho and para directing. So that means that the chlorine had to have come from this, from our probe here. So that means that chlorine was the final kind of stage, so to speak. So we added on, basically what I'm trying to say is we added on the chlorine after we added on this other group here. So how do you add a chlorine to, or I guess actually, let's see, we have to make this a donating group. I mean, a withdrawing group first, really. That's what we have to do. So we have to make this a withdrawing group to put this on here, right? And so this has to stay a withdrawing group before, like this has to stay a withdrawing group so that this can come on, right? So basically what we would have is whatever our decision is, right, is like the step before it is that the chlorine wasn't here, right? So how would we turn this one into a withdrawing group, right? This one up here, how do we turn that into a withdrawing group? So that means that this has to be less electronegative than the next whatever atom, right? This one, obviously, it's the same electronegativity. So, you know, we have this oxygen. How we do that, how we go from, remember how we totally reduce our ketone off, remember, is that zinc, mercury, HCl, right? We talked about it back here, a little bit further back, Okay, right here. Remember we did the same thing here, right? So there's zinc, HCl, right? So that's how we took off our ketone there. And so then, you know, backtrack here. So now we have this withdrawing group, which allows us to have this meta position, right, for this chlorine. So that means that this also had to have been here, right? Because we didn't get rid of it until up here. So we have this position. Now, how do we get this chlorine on there? What kind of reagent will we use just to get like a chlorination, right? This is our, just as a reminder, Alfredo Kraft's acylation. Okay. But yeah, so what do we have to do to get a chlorine on there? What are our reagents that we know to put the chlorine on there?
Were you asked? Oh, okay, never mind.
Oh yeah, no, I'm asking everybody. I'm asking all of you. Definitely
Okay, I was gonna
participate.
say,
Yeah.
I was gonna say HCl, but I completely misunderstood the question.
No, you're good. You're good. Yeah. Yeah. So, you know, you just have to think back about, that's why like having your reaction summaries in front of you when you're working these out in the beginning is very, very helpful. So that way you don't get stuck with anything, right? So how do we know how to add, how do we know how to like do some sort of like chlorination reaction, right? So, this was back, I think last semester, last like OChem 1, I think is those reactions. I'm just trying to double check. Retrosynthesis reactions. I just wanted to be able to give you guys a page to reference, but I cannot find it. Yeah, anyway. So yeah, gosh, I thought it was right here. I just can't find it. Anyway, so then what are we using to put this on there? Right? So like, what did we add? Oh, let me add these things. What did we add? You know, what is, you know, this piece here? This is what we added, right? We added this.
A ketone?
Yeah. Yeah, so we had to have added some sort of, you know, so I'm just going to draw this part first, right? But how do we add this to this? Like, what do we have to do? What's a useful reaction to get that on there? Oh, these are on page 16 in benzenes. They're at the, this is all at the end of, so if any of you guys have your gap notes, go to page 16 in the benzenes, the last page. It's the last page of what you guys have covered, I believe, for this section. So how, and it's kind of, it's right in there, right? It's a fructose acylation. So what do we have to do? What's a fructose acylation? How do we do that? Right? We have to add a Cl and then, you know, slash AlCl3, right? So we added on there. Okay, because remember we have that hydrogen here, and the Cl comes on and takes this off, and then this, you know, this will come here, right? And that's how we have this bond here. Okay, so there's our little synthesis. Any questions about this one?
No, I think I'm okay.
All righty. Okay. Next, what do we have? What do you guys think? What do you think could be, you know, first steps? What are we thinking about? So what we've done is we've added these two groups again, right? So what's this amine group? Is it a donating group or withdrawing group? This is the donating group, and then your chlorine, it's a halogen, right? So technically it's a withdrawing group, but it does donate through resonance, right? Because it's more electronegative, right? But it does donate through resonance. And so, but halogens, like I said, will always be ortho and para directing. So your halogens, ortho and para directing, remember halogens, fluorine, chlorine, bromine, iodine, right? Those are the ones that we see, right? So this is ortho and this is para. So is that nitrile group on, or amine group, excuse me, on either of those positions?
No.
Yeah, so it can't, we couldn't have added this from this. So we had to have added this one last, right? We had to have had this one first so that we could add on this chlorine. Donates through resonance, right? So that means that we had the nitrile one first. Well, and do we know any way, the amine, excuse me, keep saying that. Do we know any way to just add an amine on? Do we have any reagents that just add amines? The answer is no, we do not, right? So how do we get an amine? So we've already decided that this chlorine, how do we get an amine? This has to say a withdrawing group. I mean, excuse me, this has to say, yeah, yes, a withdrawing group. So this is a meta position, right? Here's a hint to this, right? This is a meta position. This is a donating group. A donating group is not going to put this chlorine on in a meta position, which means that at some point this had to have been a withdrawing group, right? So not only do we not have a way to just add an amine, but we also really need to have a withdrawing group. So what is the alternative withdrawing group of an amine? Look at your summary, your reaction summaries, right? And see if there's something on there that like looks similar to an amine, but is actually a withdrawing group. On page 16, benzenes.
NO2.
Yeah, exactly, NO2. So we know that we had NO2. So how do we reduce NO2 to NH2?
You add H2 and PDC.
Yeah, whoops. Yeah, exactly, H2PDC, there we go, right? That's how we get that. So now what? So now we have our withdrawing group to put our chlorine on there. So how do we put a chlorine on there? So now we know we have, right? We have this, there's our NO2. So what do we have to do to put a chlorine on there?
You add Cl2.
Yeah, Cl2 and what?
AlCl3.
Yep, AlCl3 or FeCl3, either one, right? Either one. Okay, so now what? How did we go? How do we go from our benzene to our nitro dioxide? How did we do that?
You start with HNO3 and then H2SO4.
Yeah, it's our catalyst, right? It's what makes the reaction go. Need a little oomph, right? Does this make sense? How's everybody feeling about this? These are some of the ways that you got to think about this. Unfortunately, I would love to tell you that this will go away, but it's not going to. You're going to see it for the rest of this semester, session, whatever. These synthesis problems, like if Professor Nedelkova is nice, you won't have 6-step reactions, but Dr. Pillai did 6 and 7-step reactions. So it's definitely, I highly suggested that you practice this and start thinking about ways in which you would solve these. Because as you can see, this is only a 3-step reaction, right? So imagine doubling that. So C, what are we doing? What 3 things have we done? Right, we've added these 3 items. Okay, so do we have a 1-step synthesis, aka a direct way of adding SO3H? Do we know of a 1-step reaction to do that? Yes, we do.
Oh, okay. Sorry.
No, you're fine. No, hop in. What about bromine? Do we know about a 1-step reaction that'll add a bromine?
Yeah, so you would put BR2
It
and
depends. There's a couple different ways, but
or
yeah, we know that there's ways. There's many ways. That was one of the first syntheses that we did, was to add bromine, brom. And then what about carboxylic acid? Do we have any single step ways to do that? No, this is a
I'm not
multi-synthesis. Yeah, it's a
Oh.
multi-synthesis, right? Yeah. So, okay, so then let's determine, so we have, let's see, these two are para from each other, right? These are ortho from each other. And then these two are meta from each other, right? So we know that this is going to be to add these. So we're going to want to start with, some sort of, well, you could go both ways, right? But so you know that this one's going to be like a multi-step synthesis, right? So if we wanted to get carboxylic acid, what do you have to do? Like, where does that come from? What are some of the, what's the way that we get carboxylic acid? Well, you have to start with what? You have to start with a methyl group, right? And then what do we do? What's the two-part step to get carboxylic acid? Is it our acid workup step? Remember? It oxidizes it. Ringing a bell? Okay, so that's our step. That's our step there. Okay, then what? Okay, so now what do we have, right? So we have still this is what? Our methyl group is what? Donating or withdrawing?
donating.
Yep, donating group, which means what positions would it place another group in?
The meta position.
Orthopara.
Oh, okay.
This is our bromine is what?
It's ortho.
Sorry, what I meant was, is it a donating group or withdrawing group?
Oh, okay. Withdrawing.
Yeah, technically it's, yes, withdrawn. Well, technically it's a deactivator, right? So any halogen is a deactivator because it's highly electronegative in a large molecule, right? So it will deactivate your ring, because it'll pull the electrons towards it because it can hold up to 8, right? But it will typically donate in an orthopara position, right? Deactivator. And then, so what about our SO3H? Withdrawing or donating? This is a withdrawing group, right? So that means meta. And so this is, so meta position means that it would have to have something going here. But again, remember, we have a donating group, so we're going to listen to that over a withdrawing group, right? So with our donating group, we have ortho and para positions, right? So this is meta, right? This is a meta position, whereas this is orthopara, right? And this is also what's considered orthopara, right? So we still have that same kind of positioning. So obviously we're going to listen to our donating group first. So that means that we're going to be adding our SO3H, right? So what do we have to do to add SO3H? So we've decided that we didn't have this before. So we can go ahead and draw this in. Right, so we want to add this group here. So how do we do that? What reagent do we need to add that? And it's on your reaction summary.
Okay. I'm sorry.
Yeah. No,
My
you're
answer's so
good.
slow.
No, you're fine. I just, I don't want to like sit here and tell you guys everything because nobody's
Yeah.
going to tell you it on the exam, So yeah, so we've knocked down at least, we've reduced one, well, yeah, reduced one and we've gotten rid of another one, right? So now what? So what's next? So we've already decided that this is going to donate in an ortho and para position as a deactivator, but our methyl group is in neither an ortho or a para position. So these two are meta from each other, which means that this had to have been at one point a what? What places things in a meta position? Donating or withdrawing?
Withdrawing.
Yeah. So this had to have turned into a withdrawing group. So what do we do to turn it into a withdrawing group? What would it look like if it was a withdrawing group? Have to have what? You got to have some sort of electronegative atom on there that's away from the ring, right? You have to have something that's going to withdraw the electrons from it, right? So what option do we have? Right? All we have is a methyl. So the only thing we can do is oxygenate it. So what is it that we do to go from A to B? How do we do that? What's happening? Jackie, calling on you because we've talked about this a couple times now in this review. What are we doing? Right? We're getting rid of this ketone. We're getting rid of this double bond O. It's not technically a ketone, it's an aldehyde, but hopefully you understand, right? So we have to reduce it. So, and how do we do that? Remember? We've talked about it a few times now. Okay. So, then what? We've got a couple more steps to go. What else do we have? Let's see. So now that we have our withdrawing group, right? So this is officially a withdrawing group now. Then that means that we could have added this bromine in this step, which means that this step would have been, whoops, wrong way. This step would have looked like this. Okay, so how do we add this bromine?
You can use BR2 or FeBr3, I think.
Yeah, I use them both. Yeah. BR2, FeBr3. Okay. Perfect. And that's what puts that on there. I should have done the reagents in different colors. Sorry, guys. And then, so how do we add our aldehyde? What do we do to add our aldehyde?
I know you add AlCl3, and then I forgot what the first reagent was called.
Yeah, so we have this carbon and we have this hydrogen and we have this. right? And we're going to, I'm just going to put a slash notation here for the ALCL3. So what do we have to, what has to go here so that we can add it to the benzene ring? This is our Friedel-Crafts acylation. Right? You have to have your chlorine because we're using aluminum chloride, right? So yeah. So this gets added here because of this, right? And then what? This gets added here. And then this reduces our ketone to nothing. And then we add this with this, right? And then we've got all three of our functional groups, but we just need to oxidize it. So we do it with this to get that, right? So that was a longer one. 1, 2, 3, 4, 5 step. Okay. So that's all I have for the review stuff. Does anybody have any questions about it? I know that synthesis stuff, it's like, ugh, you know, I get it. So, not fun. But the more you practice, the easier it gets, I promise. I know it probably doesn't seem like it, and it seems like you're, trying to pull teeth without Novocaine. But just keep practicing it. And honestly, you can keep practicing the same one over and over again until you get really comfortable with it as well. So any more questions before I stop screen share and stop recording?
I think I'm okay. Thank you.
Yeah, so feel free, let me know if you guys have any questions. You can always send me an email. And I'm here for you. You guys will do awesome. I think the exam opens tomorrow or something. So believe in yourself. You got this, okay?
Thank you.
You're welcome.